All right, so can we get started? Okay, so the first speaker of this session is Francis Racine. Sarah Racine is going to talk about the dark matter collider. Yeah, please get started.
Hi, great. Thanks for the organizers for putting together such a great conference despite a difficult situation. So today I'll talk about some work I've done recently about constraining dark matter physics through astrophysical observation. So this is a particle in cosmology kind of crowd. So we all know there's a lot of ideas out there about what dark matter could be. So here is a brief summary of that. And of course, all of these models in one way or the other are able to reproduce all the success we have in cosmology on large cosmological scale. So they look like cold dark matter on large scales. But so if you want to distinguish any of these possibilities shown here, we're going to need to look differently because we know that on large scales, everything looks like CDM. So these models here that I've highlighted in this red ellipse are, as I said, exactly like CDM on large scales. But what's particular about those is that on smaller scale, that is, scales of galaxies or below, they tend to make different kind of predictions about the amount and the properties of structures that we observe in the universe. So these are the kind of theories here that are interesting to astrophysicists. Now, if you want to talk about the amount of structures that we have on small scales in these kind of theories, we usually do this through, of course, the matter power spectrum, which is illustrated here. And just to kind of guide the discussion here, I've indicated at the top the kind of typical mass scales of object populating the universe that we're talking about here. So these theories are interesting from a structure formation point of view, from the small scales, tend to change things on scales, as I said, below a galaxy or things below, say, 10 to the 10 or so solar mass. So these are the kind of mass scales, or in terms of physical scale here at the bottom, that we want to discuss here. So what that actually shapes the amount of structure given any kind of dark matter theory, particle theory you want to write down. And in a universe like ours, it's actually quite simple. It's always a struggle between pressure and gravity. So gravity tries to pull everything together and form bound structures and allow structures to grow, while pressure opposes gravity and try to dilute everything and push everything apart. So there's the story of structure formation in our universe is always this struggle between pressure and gravity. Now we want to kind of study this kind of scenarios in the context of dark matter. Of course, in CDM, dark matter does not have any pressure, but there are, of course, other kind of theories where dark matter can have pressure. And one example of this is if dark matter has interaction with light particles at early times. Of course, not today, but at early times, dark matter has interaction with light particles. And these light particles are, of course, relativistic at early times and will give dark matter pressure that will effectively oppose gravity and change the way structure form in our universe. Now, this is in this cartoon here. Just to illustrate how does this work. So in the universe, dark matter, of course, form these kind of gravitational potential, which is illustrated by this kind of well here. And normally, if you just had CDM or no pressure support, things just fall into these potentials and make these potential grow. Now, if you do have this kind of pressure support, or you're coupling to something that has pressure, this pressure would effectively oppose this gravitational infold and gives rise to what's illustrated as springs here. That will prevent too much dark matter to fall into these wells, and the solution to these such scenarios, if you look at the equation of motion, are basically acoustic waves, and we call this phenomena. Since it's in the context of dark matter, we call this dark acoustic oscillation. In total analogy with what happened, of course, in the real sector, where baryons and photons are coupled in the early universe, and there's also a acoustic wave solution, which we of course call baryon acoustic oscillation. Now, kind of the important quantity, of course, that control the amount of pressure that oppose this kind of gravitational pull is controlled by basically the temperature of this dark radiation, whatever it might be. And we tend to parameterize this by this ratio of this dark sector temperature, TD over TCMB. And a natural value for this, if you assume something, say, with couple above the weak scale, is like a half or so. So generally speaking, the dark sector is colder than the standard model. So if you want more kind of concrete example of these kind of models where you do have such coupling between dark matter and something relativistic at early times, here are two examples for you. One is maybe the simplest one is some kind of charged dark matter that's coupled to a dark Q1 with a nearly massless or massless dark photon that is relativistic. Will give rise to this Compton-like interaction, which eventually kind of pressurize your dark matter at early times. Another kind of poster child example of this is a Yukawa type of interaction where dark matter interact via a massive mediator to something that is very light, like a sterile neutrinos or some other very light fermion, which effectively also will give dark matter some pressure via this kind of T-channel interactions. So if you kind of turn to crank and look at the evolution equation and look at what kind of structure you end up in the linear regime, you can make these transfer function plots. This is basically illustrating the matter power spectrum, if you want, divided by that as CDM. And not too surprisingly, since you got this acoustic physics going on at early times of these model because of this pressure support, this matter power spectrum and transfer function ends up having these oscillations in them, which are these dark acoustic oscillation coming from this pressure support. And as we can see from here, both on the left and the right, there's quite a broad variety of structure that we can have for this acoustic behavior. So on the left, I illustrated something I call weak DAO, which is oscillation caused by this pressure. They are rapidly decaying with scales. So here the x-axis is wave number. So this is small scale, this is large scales. So in the weak DO, these oscillations tend to decay quite fast because the coupling, say, between the radiation and dark matter is kind of weak. So it gives rise to a lot of dissipation at these epoch. You can also have other regime, which I'll call here the strong DAO. And this is the regime where things are very strongly coupled. So it gives rise to these oscillations or these acoustic waves, if you want. They are very well defined in the transfer function or the matter power spectrum here, and are undamped for quite a while until you reach some diffusion scale that gives rise to this damping envelope. So you can have a regime over over an order of magnitude in scale where you can have this undamped oscillation whose amplitude can even go, say, above the level of CDM in terms of amplitude. So that's quite interesting. Now the question, of course, that you might have is what determines the shape of these oscillations, or the shape of the matter power spectrum. And it's basically very similar to what gives rise to the structure of the cosmic microwave background, which, as cosmologists, we're quite familiar with. And really the quantity that matters here for determining the shape of this matter power spectrum is what we call here the dark matter drag visibility function. And its visibility function is basically a probability distribution for when dark matter last scatter of this dark radiation, dark photon, or whatever you have. And depending on the shape of this probability distribution, which I illustrate some example here on the left, you can have broader shape or narrower shape. And the point here is that the broader the shape of this function is, the more damping you get in the matter power spectrum of these oscillations, the more these oscillations are damped. And the narrower is this function, the less damped and the more well-defined these oscillations actually are. So these N here that I have on the legend correspond to how fast is this interaction rate, the momentum transfer rate, if you want, between the dark matter and the dark radiation actually scale with the redshift or the scale factor describing the expansion of the universe. And a faster rate compared to the Hubble rate correspond here to a larger N in this a more narrow visibility function. So kind of the lesson here is that if you do have these kind of particle interaction going on in the dark sector at early times, there's a new scale that appears in a problem just because of these interaction. And of course, this scale, of course, is this DAO scale, this dark acoustic oscillation scale that correspond to these how far the sound wave travel in the dark medium before decoupling happened in the dark sector. Of course, this is all in theory. So a good question to ask is whether we can actually detect these things. And this is some work I've done recently with William Munoz at Harvard and my longtime collaborator. He was Zavala and Sebastian Bohr in Iceland. And just to introduce a notation I'll be showing, in the remaining couple of minutes here, we'll be talking about these model that have these oscillation, and we'll be talking about two parameters, which is K peak and H peak. And it's very simple. K peak tells you where this oscillation, which wave number this oscillation is actually happening, this first bump here. And H peak is basically the height of this bump, where one basically corresponds to kind of CDM level of fluctuation. So what kind of observable we could actually use to learn about these interaction and these DAOs that get impacted on the matter power spectrum. And since, of course, everything here, as I said at the beginning, happens on very large scales, on the scale smaller than galaxies, we're deep here in a non-linear regime. So what we want to talk about is the halo mass function, the number of bound dark matter objects we have in the universe as a function of time and mass. And the quantity that matters most, for understanding the behavior of this mass function is this mass variance, which I've highlighted in red here, and that's some integral over the power spectrum, which is, what I was just showing before, the linear power spectrum. So this power spectrum has oscillation. As you do this integral, you're going to pick up this behavior from this oscillation. Now, if you do that, it's kind of the cartoon version of this here is kind of shown. So this is the mass function. It's a function of actual mass and solar mass. And in blues is the case you're familiar with, just from CDM. This is just a power law, no scale model, basically, with a slope near -2. And maybe another model you've seen before is warm dark matter, which we suppress structure below a certain scale. So this is in red. And in these other lines here, I'm illustrating, these ideas I would just introduce to you in terms of DAOs and what these mass function actually looks like. And it's kind of interesting in the sense that they have very different shape than either, say, CDM or warm dark matter. They have this behavior, they tend to deviate from CDM, say like warm dark matter, but then they kind of turn over and start tracking CDM or being close to CDM for a while before eventually get damped. So this is kind of a behavior that's very different than what we've seen before. And of course, what I've shown you was just like a theoretical calculation, but now in order to test this in practice and see whether this is a real thing or not, we've actually run a big suite of simulation in these models that has these acoustic oscillations and to compute from simulation to mass function. And indeed, we observed this behavior that this mass function does deviate from CDM certain scale, but then to turnover, and how much it turns over depends on how big this peak, how big these DAOs actually are within this transfer function. So that our expectation from theory actually match what we get from simulation. And what's neat here is that we understand from theory the full redshift evolution of these mass functions. And what's interesting, if you look at this bottom kind of panel here, showing the ratio of these mass functions to that of CDM, kind of normal scenario. And what we see here is that as a function of redshift, you have this kind of this feature that grows with time, say around, here 10 to the 8 or so. And this feature is really caused by this acoustic oscillation that took place at early time. So this mass function, which is of course a very late time observable in the universe, I think we can observe it in our own galaxy by counting satellites, as memory of interaction that took place at very early times. And it shows up as a feature in the mass function, which you can see here by maybe more prominently in this theoretical calculation again, where there's really a new scale again put in the mass function, which is this bump that's really caused by some interaction that took place very long time ago in the universe. So this is kind of interesting. This is the idea of using kind of present-day observation to learn about collision or colliders that took place long in the past. And so that's nice. And you can actually use this kind of idea to distinguish, say, a warm dark matter model, something that's a simple suppression of power on small scale, to these models that have these DAOs. And this is, it's a bunch of H peak and K peak. This red region here illustrates, what kind of value you can imagine you could be able to distinguish, say, a scenario that has the DAO versus a scenario that simply has a very simple cutoff, say, caused by free streaming, like in a standard warm dark matter. So lesson number 2, the ALU mass function has actually good memory of some physical process that took a long time ago, and that shows up as a very specific scale that get imprinted in the problem. And what can you do with that? Well, there's a lot of things we're actually working on. The LO mass function, of course, feeds into a whole lot of observables in the universe, including things like 21 centimeter cosmology, the high redshift UV luminosity function that we can observe using deep images with space telescope, and of course, substructural lensing, probing the small scale structure within galaxies. So let me conclude here. So I've told you that if you do have these kind of interaction collisions at early times in the dark sector, these collisions, the memory of these collisions will show up much later on in the halo mass function. And this shows up as a very specific scale, a bump, if you want, that get imprinted in the mass function. And then the game is try to use a lot of these observables that depend on this halo mass function to try to learn about these kind of interaction and these collisions that took place long ago in the past. So thank you very much.
Thank you very much, Francis. So any questions or comments? So let's get started with a simple question. So you have a very fine detailed oscillation from dark acoustic oscillation. Can you see that fine details rather than just damping scale, amplitude?
Yes, yeah, that's a good question. So let me just go back to that. To the strong DAO case here. So there's one reason why I focus on the mass function for this talk. I could have talked a little more about directly measuring the 2-point function of the power spectrum. But of course, what happens here is that these are a very small scale, deep in the non-linear regime. And in terms of the 2-point function of the power spectrum, these DAOs tend to get erased. I do have actually simulations, plots of this where you can actually see this DAO being erased by nonlinear physics. And if I were to give the longer version of this, I'll tell you that looking at the 2-point function is not the way to go to constrain these ideas, because the nonlinear physics is very good at erasing information about on the 2-point function or the power spectrum. However, the mass function is much better at retaining memory of these effects, and that's going to be interesting. And in addition, how much the mass function remembers actually gets more and more as you go towards lower and lower redshift, because the prominence of these features kind of grows with time, which is kind of interesting, which is basically the complete opposite of what happened in the power spectrum, where things get erased as you move forward in time. In the mass function, it's the other way. Things get more and more imprinted as you go forward in time, which is kind of interesting.
Thank you. Any other comments or questions? Four minutes left. So if you go to very high K, what's the good observables?
Right. So actually, I kind of just flashed three. Yeah, I just flashed 3 cases here, and to some extent, some of this is work in progress, but some of this we've done enough work that I can actually comment on this. Of all these 3 different probes, the lensing one is that allows you to go to smaller K. In probing these kind of scenarios, just because if you look at say the 21 centimeter or the luminosity function, of course these are basically galaxies. So these things are they have to form stars. So they tend to be bigger halos, so bigger mass. While of course in lensing you can actually probe things are dark. It doesn't have to contain stars for you to probe it. So the lensing is of course something that we've been working on, and a lot of people are working on, just because exactly you can probe very small scale with it.
What kind of K range you have in your mind?
Which kind of what? Sorry.
K range you have in your mind?
Yeah. So if I go back if I phrase it as a K range, let me go back to my power spectrum here.
100.
Yeah. I mean, it's already the constraint that we have from say one dark matter. You kind of these kind of things have to happen at K of 40 or 50 or above in these units, H over megaparsec. And we're talking about say maybe going from K of 50 all the way to K of a few hundred. which doesn't appear to be like that much in K. It's about an order of magnitude or so. But of course, we have to remember that mass scale as K cubed, or K to the minus 3. So an order of magnitude in K corresponds to 3 is the order of magnitude in mass. So it's a big range in terms of mass scales. Yeah.
Okay. Thank you.
Yep.
Any other questions from other people? You can just type in the chat or maybe you can speak up. Maybe the time is up. So thank you very much for my talk. Yeah.
Okay, great. Let me stop the share.
Thank you very much. Okay, the next speaker is Jacob Liedem.
Yep, that's
Can
right.
you
share my screen?
Yeah, can you?
Yes, 1 second.
Yeah.
All right, can you see this?
Yes.
Okay, great. All right, let me know when I should begin.
The next speaker is Jacob Liedem, and Jacob is going to talk about ultralight action.
Yes, thank you. Thank you everyone for coming. And of course, thank you to the organizers for the opportunity to talk. Today, I'm going to describe some work I did with Jeff Dror on the cosmological tension of ultralight axion dark matter and its solutions. So, let me, oops. Okay, there we go. All right, so we've already had a number of talks on axions and dark matter in this conference, so I'm just going to stick to some essentials for the beginning of this talk. So I'm going to focus on ultralight dark matter here. So for the purposes of this talk, I'll define that to be around 10 to the negative 22 to 10 to the negative 13 eV. And of course, this includes the so-called fuzzy dark matter regime of around 10 to the negative 21 or so eV. And so this is going to be this boson is going to be an axion, and so I would consider this dark matter particle to be the Goldstone boson that results from the breaking of some global symmetry, or perhaps the zero form of some higher formed field. And of course, the benefit here is that this field will have a continuous shift symmetry, which will naturally give an explanation for its very small mass. Now, of course, there's going to be some non-perturbative effects that will break this continuous shift symmetry down to a discrete shift symmetry, so that will generate a potential and, of course, a mass then for this ultralight axion dark matter. And I'll parameterize that in the usual way of just a simple cosine, at least for most of this talk. And so there'll be some scale mu out in front, and then the axion decay constant Fa. And then the mass is approximately mu squared over Fa. And so the purpose of the talk today will be to derive bounds on ultralight axion dark matter from the matter power spectrum. And then I will also describe in the second half model building techniques to at least partially evade these bounds. All right, so these bounds are going to show up in the parameter space of couplings of the ultralight axion dark matter to the standard model, because that's what we're interested in measuring here. And so I'll consider the axion photon coupling, which has the usual form with FF tilde, so F being the electromagnetic field strength. And then I'll also be considering the axion nucleon coupling. So this is the usual derivative coupling to neutrons and protons. And here I've also defined some model-dependent parameters, Ca gamma and Can. So these should generically be some order 1 parameters that depend on the details of the model. And I'll get into more discussion on that later. You can consider other couplings. So for example, electron or muon couplings. But for today, we're just going to consider photons and nucleons. All right, so first, let's look at what this parameter space, some features of it. So you, of course, have the lower bound from Lyman alpha at about 10 to the negative 21 eV. So technically, there's a number of interesting recent results that shift this around a little bit, but for the sake of just keeping things clean, I'll put it at 10 to the negative 21. But of course, just look at the paper for the more detailed description. And then there's an upper bound on the axion photon coupling from supernova 1987A. Now we can fill in this parameter space with some existing and future bounds. So solid lines correspond to existing bounds, and then dashed lines correspond to future ones. So here you've got various contributions. So protoplanetary disks, CMB birefringence, active galactic nuclei, and then eventually pulsars and optical rings that are going to be filled in here. And you can do the same thing for the nucleon coupling. So you've got Lyman alpha in 1987A. And then a whole bunch of future probes in this parameter space involving storage rings, comagnetometers, atomic interferometry, and then Casper. And so the purpose of what we're going to describe is placing some constraints inside of this parameter space. So first, I'll go through kind of a back of the envelope sort of way to motivate this, and then give a little bit better description from some numerical considerations. So let's consider just some scalar field phi, whose potential is phi to the n. We have the usual kind of relationship between pressure and energy density, and then the relationship between energy density and the scale factor. Now, if we just consider some cold dark matter scenario, the energy density is going to dilute as r to the -3, and this corresponds to just a quadratic potential, so phi squared here. Which is related to the scale invariant matter power spectrum. Now we can add kind of a quartic perturbation to this. So we'll just add a lambda a to the 4th, for instance, and then using the constraint at matter radiation equality on the perturbations on the energy density over the energy density itself, we can kind of wave our hands a little bit and say that the perturbations are given by the quartic term, and then the dominant part of the energy density is given by the quadratic term, and then we get kind of a rough looking bound, something like this. So we can apply that directly to the ultralight axion dark matter. Again, we're going to parameterize that as a simple cosine, expand that out, and you get a quadratic and a quartic. And then putting in information, again, we're assuming that this is going to be actually be dark matter. So using that information and then plugging in everything into this kind of rough description on the previous slide, we come to the following bound at the bottom, which I call the rough cosmological bound. So this is relating essentially the product of the axion mass times the axion decay constant, and is providing a lower bound for this quantity right here. So again, this is kind of a back of the envelope, quick little thing, but you can do a much more rigorous description of this. In particular, we can lift some results from this paper here by Poulin and company. So I won't go into too much of an in-depth description, but the essentials are that in order for these this ultralight axion dark matter with this cosine potential to be a viable model, you have a lower bound essentially on the redshift at which this thing, the scalar field started oscillating. So that occurs at about redshift of, the redshift has to be greater than about 10 to the 5. So again, assuming that the axion is dark matter and that the dark matter density is dominantly given by the quadratic term, and then using information about the how the amplitude changes with the redshift, we can again arrive at a very similar looking bound, again, a lower bound on the axion mass and decay constant, which I'll call the numerical cosmological bound. So this is very similar to the one that I just given from the back of the envelope description up to some fudge factor to get things right. So in what follows, I'll be using the much more rigorous bound, but it's nice that you can kind of do a very simple argument to get to this bound as well without having to go through the numerics. All right, so let's begin putting this onto the parameter space and seeing the influence of this bound. So here I've plotted the bound in the axion photon coupling parameter space as this black line. Now, in order to do this, I had to make some assumptions on these model-dependent parameters I described earlier. So in this case, what I've done is set that Ca gamma coupling to 1, and so the matter the matter power spectrum bound would then rule out the region of parameter space to the left of this line. So we would expect that if you want ultralight axion dark matter, sort of a generic model to be viable, you have to exist on the right-hand side of this line. However, you can maybe loosen up your philosophy with regards to what Ca gamma should be. And so, for instance, you could jump it up to maybe 10 to the 2 or 10 to the 4, and you can see that the bound actually weakens as this grows. So I'll get more into that in a little bit here, but you can at least see the effect of what happens when you change Ca gamma around. You can also get a bound from if you assume that the ultra axion dark matter is populated just from the misalignment mechanism. You can get a very different sort of bound that was produced earlier by different authors. So I'll just add that here as well. And one can do the same thing in the axion nucleon coupling parameter space. So here you have contours for CAN equal 1, 10 to the 2, and 10 to the 4. And again, the misalignment bound. So The key takeaway here is that the matter power spectrum bound cuts deeply into the parameter space that many of these experiments are looking at. So here we're cutting away quite a bit of the parameter space for these experiments, and a similar sort of thing in the previous slide. In fact, the entire kind of parameter space of the pulsar and CMB birefringence section here are ruled out. So one can ask the question, is there anything that can be done to try and justify these parameter spaces, in particular, really pump up these coupling constants? So we can ask the question, what are the experiments actually looking for here? And so you've kind of gotten a hint of what's going on. What you want to do is introduce some non-trivial Malda building in order to pump up the coupling Ca gamma and Can. So that's what I'll describe in the second half of this talk, which is various strategies to try and do that. Luckily, this has been discussed in the literature a lot with applications to QCD axions and axion inflation models. So what we'll do is just take those strategies and apply them here and see how far we can get. So to answer this question, these experiments are kind of looking for a Rube Goldberg axion model where you need to do some additional model building in order to be detectable. So you need to add some bells and whistles to these things for it to work out. So the kind of obvious thing that you can do is to try and adjust the fermion content. So for example, you can try and introduce more fermions, or you can adjust the charges of the fermions. And so that seems like a viable method, but there's a little bit of difficulty here. If you write down this vacuum polarization diagram, you're going to have these fermions that are running the loop. And so in order to actually keep permittivity of this theory, you actually need this combination of constants over here to be less than 1. And so what you can do is you basically get a bound of about 10 to the 2 as the upper bound on the enhancement factor that you can get from this method. Another possible strategy is kinetic mixing between two different axions. So here I've got A1 and A2 and then a kinetic mixing term. And then A1 here will actually get the cosine potential, and then A2 is the axion that will be coupled to electromagnetism. So just doing a shift redefinition, you can get rid of this mixing term. And what will happen is that you get a photon coupling with A1, and you'll get this factor out in front, epsilon F1 over F2. So if this factor is much greater than 1, then you've achieved your goal, and the axion photon coupling is enhanced. So that seems fine. But it turns out that this is not really an easy thing to do within field theory. So I'm not going to go into the details here because it's just a little bit more involved. But I'm happy to answer a question about it. But essentially, if you try simple field theory constructions, you're never going to get actually an enhancement factor. You just get some factor out in front that does not evade these bounds whatsoever. Now, there are some statements in the literature that possibly some string constructions could help you, but so far, as far as I know, there's no solid model that would do this. So for the moment, I'll just say that this doesn't seem to work. So you can get a little bit more involved as well and consider a discrete symmetry. So this is essentially a strategy that was looked at by Ants and Hook in this paper here in a slightly different context. But what you do is you introduce one axion and then n non-abelian confining gauge sectors with field strength G sub n. And so the discrete symmetry relates these various sectors, and then there's a shift for the axion as well. Now, here, we're going to deviate a little bit from this description of the axion potential as just a simple cosine. The reason for that is that if I put a simple cosine in here and then I do this sum, a trigonometric identity just gives me 0, actually. So that's not viable. Instead, what you have to do is be a little bit more sophisticated so you can get some inspiration from, for instance, chiral perturbation theory. And we can think of having some quarks with some masses that this factor z depends on in this square root. And we can parameterize the axion potential in this way. So if you do that, you can expand it out to a quadratic and a quartic term, and then you get the axion photon coupling here in terms of C2. And now you can look at how these things grow with n. So as n increases, C2 decreases, which is good. That gives you an enhancement that you're looking for. C4 also decreases, which is fine. But the problem, though, is that C4 over C2 actually grows with n. So if you recall back to that back of the envelope calculation for the matter power spectrum bound, that involves the quartic over the quadratic. And so what happens actually here is that the matter power spectrum bound gets stronger as you try to go to larger n rather than weaker. So you can try and enhance the photon to the coupling to the photon, excuse me, but at doing so actually brings you into trouble with the matter power spectrum bound. So this is actually not a viable method for enhancing the coupling. So finally, I'll discuss a clockwork setup. So here we're introducing n axions and then n non-abelian confining gauge sectors. So somewhat similar to the previous slide, but we're not introducing any kind of discrete symmetry. So we've got a somewhat peculiar structure here with a sum of the various axion fields, and we introduce a coupling constant beta. And then we also distinguish A1 and AN. So A1 is the only axion that couples to G1, G1 tilde, and then AN is the only axion that couples to photons. And so here we'll go back to our simple cosine potential since we don't run into any trouble with just getting zero. And so what you can do is under certain assumptions of the various scales involved, you can integrate out the heavy axions. And so that the remaining axion will be primarily the A sub n that we started with. And then you get an enhancement factor here of just the product of all the various betas. And so even with a modest beta, so something order 1, if you have enough sectors, so n is large enough, then you can get some enhancement here. And so this actually seems to work. You can get your enhancement. The only caveat here is that perhaps not in all UV completions, you can just keep adding sectors. So that's the only caveat to this strategy right here. All right, and so now I will conclude. So in the first part of the talk, I discussed bounds from the matter power spectrum on ultra axion dark matter models. And then we kind of asked the question, can you model build out of these bounds, or at least to some extent? And so the answer is that for some strategies you can and some that you can't. So large charges or lots of fermions, this is of limited effectiveness. Kinetic mixing doesn't seem to work from the EFT perspective, but again, perhaps some string constructions could work, but I'll mention again that as far as I know, there isn't a solid model to do that. For discrete symmetry, this unfortunately doesn't work, and clockwork is viable so long as you're comfortable just keep adding sectors into your theory to pump up the coupling. And that's it. Thank you. Oh, I think you're muted.
Thank you very much, Jacob. So any other questions or comments? You can just type in the chat section. Yeah. Oh, there's one question. Can you read, Jacob?
Yes. What is the for the ALP?
Can you repeat the question and give answer?
Oh, sorry. Could you repeat that?
Can you repeat the question and can you
yeah,
answer?
sorry. Yes. I may have missed it. What is the implication for the ALP explanation for Minami Komatsu? Sorry, I'm not sure I understand the question. Could you please expand on that? What is the implication? Oh, okay. So, you mean what parameter space is affected by that? So if I scroll back here, is this what you're asking for?
Yeah, that's essentially it. So,
yeah, okay, gotcha.
Can you like square your results with what Minami and Komatsu have? There's like follow-up papers by, I guess, who's it, Tsujikawa et al., who give an ALP explanation for this. It's even in the original PRL letter, right? So, so anything to say about this?
Sorry, so yeah, can you please describe exactly what the further about your question? So, I mean, so are you saying that they're describing that they should have a signal here, or yeah?
So basically, it seems like you would be placing quite strong bounds. So okay, so they've definitely seen something in Planck data at 2.4 sigma, right? So then the question is could that be an ALP? I don't know if it's ultralight or not, or but you seem to be eating up some of their parameter space.
Right. Yeah.
Is
right.
that possible?
Sorry. Go ahead. Oh, was that the end?
Yeah, that was it. Basically,
I mean, yeah. So I'm trying to think about potential ways around it, but I mean, so what I could say is that if so I guess the most broad statement that I could make then is that with sufficient Malda building, you could be able to get into this parameter space here for the birefringence. So if you can get into, for instance, a CA gamma of 10 to the 4, then perhaps you can get to the birefringence region of parameter space only barely. However, I mean, basically, you would have to you have to completely abandon the notion that this thing would be due to misalignment, right? Because this bounds that that we derived here are just from the matter power spectrum. But if you assume further that you have misalignment, that also places very stringent constraints here. So what you would have to do is that such an axion, if to be dark matter, it would have to be populated from some mechanism that isn't misalignment. And then on top of that, you would also have to have all of this model building in order to get to this birefringence parameter space.
All right, thanks.
Yeah, great question. Thank you.
Any other quick comments or questions? I think it's almost past time now to pass to the next speaker. And thank you very much, Jacob.
Thank you.
Yeah, thank you very much. Keeping on time too. Then the next speaker is Lucy Boda. Can you share the screen?
Yeah.
And Lucy is going to talk about the cosmological collider.
Okay.
Please get started. Yeah.
Okay. Hi, everyone. I'm really happy to be here. Today, I'll talk about cosmological collider physics beyond the Hubble scale. This work was done in collaboration with Shavik Kumar and Raman Sundram. And for more details, you can look at this archive reference. Okay. So we know that the universe is homogeneous with very small inhomogeneities, as can be seen in experiments like CMB and large-scale structures. And the most compelling and minimal explanation we have is that these fluctuations were seeded by the quantum fluctuations of the inflaton field that sources inflation. And why we think that is because of some of the properties of these fluctuations. So we know that they are mostly scale invariant. At least the primordial one, I'm referring to the primordial one. They're adiabatic, and the probability distribution of these fluctuations is Gaussian, which all can be simply explained by quantum fluctuations of a scalar field in a quasi-de Sitter spacetime. To kind of connect it to in a more diagrammatic way, as we do in particle physics, we can think about just like a propagator of a real scalar and its correlation at the boundaries when the inflation ends. Here the R is actually the curvature perturbation. In some sense, it's the fluctuation of the inflaton, which is sourcing CMB or LSS or all these density fluctuations. So the point I want to make is that if there is any new physics that affects the statistics of these quantum fluctuations, then it will also show up in the statistics of macroscopic observables like we see in CMB or LSS. So these experiments actually act as a detector of physics at really high energies. And by high energies, that means the energy scale at which inflation is expected to occur, which is around 10 to the power 13 GeV, which is very exciting. So one of the ways that these new interactions can change the statistics is by imparting non-Gaussianities through interactions. So as I said, the simplest scenario is that there is a single free scalar field and its quantum fluctuations are just completely described by the 2-point function of this scalar field, which gives us Gaussian statistics. But if you have any small interaction, then it can impart higher endpoint functions. Here I'm showing one way to get 3-point function, basically. And this will impart like higher endpoint functions, more specifically 3-point functions or correlation functions, and which leads to a non-Gaussianity in the statistics. Of course, I'm talking about, I'll be mostly using the Fourier, the 3 correlation functions in the Fourier space, which is easier to work with. And of course, there is momentum conservation. So we have this constraint that all the 3 momenta should add up to 0. If some of you are more familiar with thinking about the angular scale for a 2D map like CMB, roughly, I would say there's like you can convert back and forth using the conformal distance between us and the CMB surface or something like that. So the K you can literally almost like think in terms of angular scale as well. So there can be various types of interactions, and the one I would like to focus on is the interaction which is mediated by a heavy field. And why that is interesting is that because it appears that a heavy field mediating a 3-point function, when it's produced during the inflation, leaves a very unique non-analytic signature in higher endpoint functions. And just to kind of give a visual for it, imagine like a 3-point correlation function, which is mediated by a heavy field sigma. And it turns out that if you consider a specific configuration of the momenta where 2 of the momenta are really large and 1 is quite small as compared to the other 2, then in this limit, the 3-point correlation function has a very unique form. And some of the interesting features are that there is this interesting non-analytic dependence on the mass. And if you look at it, it basically, if I plot this function as a ratio of k1 over k3, I will actually literally see oscillations where the frequency depends on the mass of this field. And there's another interesting signature, which is this dependence on the angle between k1 and k3 momenta, which tells you about the spin of the particle. So this is great. So what this tells me is that if I see such a signature, then I can actually extract the mass and the spin of the particle at this really heavy scale. So this signature actually acts as like a detector of really heavy fields. But there's a huge caveat that for fields which are heavier than the inflationary Hubble scale, there is this exponential suppression which accompanies the signal. So the signal becomes really, really small very quickly. And to kind of give an intuition of why this happens is, so basically we are producing this heavy fields out of vacuum. So that's only possible because the space-time has a time dependence, it's expanding. So technically I should be able to only borrow the amount of energy I can borrow from this expanding background is the rate at which space-time is expanding, which is the Hubble scale during inflation, which means that if I want to borrow any more energy than the Hubble scale, I will have to pay the Boltzmann-like price, which is this exponential suppression. And to give you an idea of how quickly this exponential suppression kills us is that in this plot I'm showing on the x-axis the mass of this heavy field as compared to the Hubble scale during inflation and some kind of measure of the 3-point function. And to give you an idea that with some very futuristic experiments, we have like sensitivity above this line. And you can see even at 3 times Hubble, the signal is already very weak. Now, this is, of course, like a very vague sense, just to tell you that this Boltzmann suppression is actually very strong. Another factor is that if the mass is actually smaller than the Hubble scale, then this distinctive oscillatory signature kind of disappears and the signal becomes more analytic. So basically what that tells me is that the signature will only show up if I have a heavy field in a very narrow range, and which kind of limits our reach of new physics. So the question is, do we always have to suffer this Boltzmann suppression, or is there some mechanism or are there models in which we can get around the Boltzmann suppression? And one idea that comes to mind is we were getting limited because the only source available for the production of these particles was the background expansion, which had Hubble scale. So if I can instead find another source for the production of these particles, which is maybe higher than the Hubble scale, then I can produce heavier particles. And kind of giving a more thermal analogy, it's sort of like saying if I have a chemical potential, then I can essentially, create particles which are greater than the temperature without suffering Boltzmann suppression. So that's kind of what we want. And I will now describe one model in which you can basically implement this chemical potential like idea. So I'll consider a simple case where it's the heavy field is actually a complex scalar field. And I want to couple it to the inflaton because that's the one affecting CMB, that's the one giving a signal. So here I have this sky field, which is a heavy complex scalar, which has some mass. And I've considered some dimension 5, dimension 6 operators coupling this scalar field to our inflaton, which is phi. I want you to focus on this specific operator, which is basically derivatively coupling the inflaton to the current of this complex scalar. And notice that inflaton has a wave, which is because inflaton is rolling very slowly, its time derivative or the kinetic energy is almost constant. So when I put the wave of this inflaton here, I basically get a constant which sits in which is putting number density of complex scalar in my Lagrangian, which looks exactly like a chemical potential, and this coefficient in front of the number density is basically our chemical potential. And with some perturbative considerations, this should be less than 60 Hubble, which is still good because it's greater than Hubble. Also notice that there is this interesting symmetry breaking term which we need, and I'll explain later why. So it's easier to work with a different basis instead of working in this basis. So I'm going to just rotate my field a little bit and get into a more comfortable basis to do all the calculations in. In this basis, the peculiar chemical potential operator changes into a phase in the symmetry breaking term, which is why the symmetry breaking is important. Otherwise, the whole effect would vanish. Just massaging this phase factor in the symmetry breaking term tells you that I basically have interaction terms where my heavy field is interacting with the inflaton, but all these interaction terms get a really high frequency factors along with them, where this frequency is essentially the chemical potential. And this is exactly the this extra source that we need to make heavy particles. Now, having also another effect is that the mass also gets contribution from the lambda. So the effective mass has the bare mass as well as the chemical potential. Now, having these fluctuations, you can compute what is the contribution to the 3-point function, and it can be done in something called as in formalism. I will not go into details. If people have questions, I'll explain more. But essentially, the diagrams kind of look like this. All I want you to see here is that because of having this chemical potential, you have a high energy source which can produce your heavy fields. So that is kind of what gets rid of the Boltzmann factor. Here I'm just showing you what the final expression looks like. We still have in our 3-point function, we still have a nice oscillatory pattern, which is good. That's the unique signature. And we see that the strength of this 3-point function is not suppressed by Boltzmann factor anymore and has this characteristic dependence on mass and lambda. So just to give you an idea how the signal might look like. So if here on the x-axis, I have the mass of this heavy field, and on the y-axis, I have the strength of this non-Gaussian signal. We see that for a large range, so for these 4 different plots are actually for different values of chemical potential. And we see that all the mass from 0 to all the way to lambda, all of this mass is now, has large non-Gaussianity and can be visible, while initially we were really getting killed in a very small mass range itself. And also just in terms of detectability, the CMB sensitivity right now is sitting here, so it's not detectable with CMB, but with future experiments like large scale structure and 21 centimeter, the signal we are getting is well within their sensitivity range, so which is good. We also have this nice oscillatory pattern. So here I'm plotting this non-Gaussian signal as a function of momentum ratio. And this is the oscillatory signature, which is characteristic of the heavy field. And we are getting it for really large fields very nicely. So that tells me that the signal, I can actually get the mass of this heavy field from such a signature. The only annoying part is that the frequency of these oscillations now also gets a contribution from chemical potential. So I will need an independent measurement of chemical potential to actually extract the mass. Fortunately, there is a nice there's a nice trick one can do to figure out the effective mass itself. It turns out that the oscillation frequency changes with the momentum ratio, which is P. P is K1 over K3, the momentum ratio. It turns out for large P, the oscillation frequency goes as the effective mass minus lambda. But for a smaller P, it is only lambda. So if I can independently find out the oscillation frequency in in small lambda regime and small P regime and large P regime, I can find out lambda and then get effective lambda from there. So that's actually is a great thing that the frequency is changing and we can actually get the effective mass in the end. I would just like to mention that this has also been done in these great works. People have also explored a similar kind of mechanism for fermions and spin-1 bosons. But there are some differences. For example, in the case of fermions, their mass reach is only like a square root of chemical potential, so up to 10 Hubbles, maybe. And in the case of bosons, you require some kind of fine tuning. Otherwise, you run into some kind of tachyonic instabilities. If anyone's interested, I can talk more about this. But yeah, so the conclusions are that cosmological collider physics is an exciting thing where you have the possibility of directly detecting fields as heavy as inflationary Hubble scale, which can be at 10 to the power 13 GeV. In this, one way to get rid of the Boltzmann suppression is to harness the kinetic energy of inflaton itself, which is the chemical potential, and it can be as large as 60 Hubbles. So we have implemented this mechanism in scalar field and also done it at a tree level, which is kind of important because generally when you try to do this thing with fermions or gauge bosons, you have to do loop calculations, which are quite difficult and analytically to keep track of. Our model predicts that there will be observable non-Gaussianity in experiments like LSS or 21 centimeter if such a mechanism is at play. So the Boltzmann suppression is there, but there is a way to get around it. Hopefully, if such mechanism is actually happening in nature, we'll be able to see really heavy fields. And the mass range can be, the masses that we would have sensitivity to can be as large as 60 Hubble based on what the value of chemical potential is, which is really large, which is like 10 to the power 15 GeV. So it's truly a high energy kind of collider. And I've also kind of sketched out schematically in the end how to effectively extract the mass of this heavy field from the data. Thank you for attention. I'll take questions if you have any.
Thank you, Arush. So any other comments or questions? Takahiro?
I saw some papers about study for fermion particle production, and in that case, the authors need to study back reaction because particles are so significantly produced. In your case, the back reaction small?
Oh yeah, that's actually a good question. So it's possible that you're probably referring to the boson, the spin-1 boson case, because there is some kind of, there can be like a large production of these particles and they can back react.
Even in the case of fermionic production.
I'm not fully aware of, because the thing with fermions is because of like Pauli exclusion principle, you don't actually get kind of condensation kind of effect with fermions. But yeah, certainly for bosons, I've definitely seen that you have to kind of tune the parameters so that you don't get into this instability. With our case, we also had to put constraints on the couplings to make sure that we're not getting any back reaction, or we're not actually we're not beyond the CMB sensitivity because we haven't detected any non-Gaussianity in CMB. So yeah, I didn't cover that part, but yeah, there are definitely constraints to make sure that there's no back reaction, and also experimental constraint from like CMB data. That's true.
I see. Thank you.
And the next question is by Jiajun.
Thanks. I want to ask about you mentioned in a slide that in the future experiment it's possible to detect such signal, especially for 21 centimeter. Can you specify which type of 21 centimeter experiment you are really referring to?
So can you repeat the last part?
So which type of 21 centimeter experiment you are really referring to?
Oh, so I think at this stage it's kind of more in theory than in practice, but we would need to have like a basically like a complete map of the 21 centimeter signal and at different redshifts to get a complete kind of 3D map of the fluctuations. And that's the kind of like a complete tomography of 21 centimeter. That's the kind of thing I'm referring to. I don't know if that answers.
Is there any requirement for the redshift range?
So if you can get data over different redshifts, then basically that just essentially gives you more number of modes, and that essentially decreases your cosmic variance. So that's why if you have a 3D map, that would give you a better sensitivity because the cosmic variance just goes down. So for example, like in CMB, we are limited. I mean, in sensitivity, we are limited at some point by cosmic variance, right? Because you have finite number of modes on this CMB surface. I think the advantage of 21 centimeter would be that if you have information at different redshifts, you effectively have not a 2D map like CMB is, but also a 3D map because you're getting a map at every redshift. And that essentially increases your number of modes by a lot and decreases the cosmic variance. Hence, your sensitivity is a lot better. That's my understanding of why 21 centimeter works better.
Okay.
Okay.
Sambo, can you give a very quick question?
Yeah, quick question is, are those all the discussion applicable for any spontaneously broken U1 gauge symmetry or global symmetry?
Oh yeah, that's a good question. So here we just considered we have a let me go back. Yeah, we have like an explicit symmetry breaking. So we have explicitly put a term, that linear term that breaks symmetry. Here, because we were not worrying about if the symmetry is broken explicitly or spontaneously, because that so we haven't considered like if the phenomenon things would be different if we consider spontaneous symmetry breaking. But yeah, that's a good.
Assuming you just didn't consider any specific model.
Yes, because we're kind of thinking about like an effective field theory kind of way, like we have this cutoff, and we just like trying to see if, what are ingredients we need to make this chemical potential kind of realize in scalar fields. So yeah, we don't have any specific like a UV model in mind here.
Okay, I see. Thank you very much.
Okay. Thanks.
Thank you very much for, I'm running, but thank you very much for the nice talk, Arush.
Thank you.
Okay, so the next speaker is Shuntaro Aoki. Shuntaro, can you put the slide?
Yeah.
And Shuntaro is going to talk about the cosmological collider.
Can you see my slide?
Yes.
Okay, let me start. Thank you for introduction and giving me this kind of opportunity. I'm Shuntaro Aoki from Chuan University. Today I'm going to talk about cosmological collider with multiple field effect. And this work is based on the paper and the collaboration with Masahide Yamaguchi. So as you know, inflationary observable the correlation function of the curvature perturbation zeta and the tensor mode gamma. And of course, they are important because they give a strong restriction on inflation models, or we can say they give a strong restriction on high energy physics. For example, the two-point correlation function and their truth give a constraint on the form of the inflaton potential. This figure shows the famous NSR plot. So you can see some of the inflation models are already excluded. And also we can consider 3 or more higher point correlation function. And from the constraint on non-Gaussian feature of CMB, we can constrain, for example, some of the model of a multivariate inflation scenario and inflation with higher derivative couplings and so on. So again, we can say the cosmological correlation function gives a strong restriction. So actually, such correlation function not only provide strong restriction on the inflation models, but also give direct information of new physics. Actually, the previous talker, Arushi, explained well about this topic, so I will briefly sketch the idea. So actually, it has been recently clear that higher point correlation function contain the robust information of, for example, mass and spin of heavy particle sigma. So this is actually relevant. The mass of the sigma is around Hubble scale and has interaction to inflaton. So this figure shows the example of 3-point correlation function which contain a real scalar sigma. So sigma is created at early times and decay to later decay to the curvature perturbation. So let me see. So of course I don't have time to explain the calculation of detail, but in the squeeze limit where the one of the 3 momentum is much smaller than the others, we get this kind of expression. So the so-called shape function, which is proportional to the 3-point correlation function, is given by this form. And you can see it's contained a specific momentum dependence, which is characterized by mu. So the definition mu is given by this here. So you can see when the mass of sigma is larger than 3h12, I mean when the mu is real, this factor gives a specific oscillation. So from such an oscillation signal, we can read off the mass of the maybe unknown particle sigma. So this is a basic idea of a cosmological collider. Actually, this is very interesting because we can explore very high energy scale. And yeah, actually the Hubble scale during inflation can be as large as 10 to 13 GeV, which is much higher than the energy scale of a terrestrial experiment. So in that sense, the cosmological collider open up a new possibility to explore the very massive particle. So actually, there are many important works related to cosmological collider, but because of time limitation, I cannot touch one by one. So if you're interested in, please check. Okay, so now we understand well about the signal of a single particle with a definite mass and spin. So as a next step, it is natural to ask what about the multiple particle case? So actually, this is not just one of the possible extension, but it's a more natural setup in a realistic situation. For example, by this paper, it is known that several standard model particle acquires masses around Hubble scale by the loop effect during inflation. And also for the case of supergravity, the so-called Hubble-induced mass appear for the scalar particle at the 3 levels. So in that sense, in those kind of model, you naturally have the masses of Hubble order. So this is a situation we have in our mind. There is one light mode that is inflaton. It has a mass like some Schroeder parameter times the Hubble scale. So this is light. And around the Hubble scale, there are several heavy particles which may be detected by cosmological collider. Okay. So let me rephrase our question in this way. So can we distinguish the single and multiple particle case? Or in other words, can we expect any specific signal which exists only in multi-field case? And the next question is a bit non-trivial, but what should we do when the masses are degenerate? So as you know, in the usual experiment, when the masses are degenerate, we need a very precise measurement to resolve the degeneracy. So what about the case of a cosmological collider? These are the questions we want to address in this work. So let me explain the setup. We consider the 3-point correlation function which contain the multiple particles. So here sigma I denote the massive scalar which are created at the early time and later decay to the curvature perturbation. So here the level I count the number of the particle. So it's run from 1 to n. And the interaction strengths are characterized by the coupling constant G and G tilde. So the important point here is they are non-diagonal in general, because we are working on the mass diagonalized basis of sigma. So in that basis, interaction has in general of diagonal element. So in the later discussion, I choose G equal G tilde just for simplicity. Okay, this is the result of the shape function in the squeeze limit. Actually, the total shape function is given by the summation of each particle contribution, Sij. So for the diagonal element, Sii, we get this kind of expression. And you can see this is same as the single particle case. But we have n fields, so they are superposed. In that sense, we may expect some non-trivial waveform because of such superposition. So next, for the off-diagonal part, we get this kind of expression. And actually, this is a completely new effect because it's content mixing from different two modes. And there's no such counterpart in the single particle system. Actually, there is a remarkable feature in the frequency. First, to focus on the blue part, you can see, for example, this part contains 2 times mu I. So remember the expression of mu. Roughly speaking, mu is mu express the mass of the heavy particle. And this contains 2 mu I, and this part contains mu I plus mu j. So both of them, I mean the blue part, can give a high frequency mode. And actually they are standard in the sense this kind of behavior already exists in the single particle system. However, not that red part. This part contains the difference between two modes, mu I minus mu j. So it can give a low frequency, or we can say it can give a modulation, which can be easily distinguished from the high frequency mode. So of course, this is specific to multiple field system because the notion of mass difference exists only in the multi-field. So in summary, we have two kinds of frequency, high frequency mode and low frequency mode. Especially the low frequency mode is important because it can be a proof of the existence of multi-field field. Okay, to see more detail, let's focus on the two field example. Then the total shape is given by this form. And furthermore, we divide the situation like this, case 1 and case 2. Case 1 does not contain mixing, but case 2 does. So as we saw before, the case 2 is a more interesting situation, but even without mixing, we expect non-trivial waveform because of superposition. So let me discuss both cases for completeness. So before going to proceed, one remark. So each shape function contains the Boltzmann suppression factor in its coefficient C. So for example, when mu1 is much smaller than mu2, we get this kind of hierarchical structure in the shape function. So the total shape is governed by the right mode, S11 in this case. This is a generic feature of cosmological collider with multiple field. Okay, let's start from the case 1. Case 1 does not contain mixing. That means G12 equals 0. And first I take a universal coupling constant. And in this case, the shape function is just a superposition of two independent modes with two different frequencies or two different masses. Then I use the green color to denote the total shape, and the red one for S11 and blue one for S22. Okay, first let me consider the situation where M1 is much smaller than 2. Then, as I said in the previous slide, the right mode dominate, then the total shape function is given by this form. So you can see the figure, this figure, I choose the parameter in this way. So you can see the green line, this is the total one, is almost governed by the red one, the right mode. And next, let's consider the degenerate case. M1 is similar to M2. In this case, the waveform of particle 1 and particle 2 are almost the same. Then the total shape is just twice of the single wave. So you can see this figure, green line is just twice of red or blue one. So from this observation, we find nothing interesting appears though a slight difference appear. Actually, in the second example, precisely speaking, the aspect ratio of the shape function is a bit different from the single particle case. So in principle, we distinguish them, but this is a minor difference. So let's look for a more interesting situation. So we have a possibility to get a non-trivial superposition if we choose the coupling constant hierarchically. So again, let me consider the case M1 is much smaller than M2, but this time I choose the coupling constant G2 to be larger than G11 so that it compensates the suppression. In this case, we get this kind of figure, and you can see the total wave, the green line, has a non-trivial form. So in this figure, I choose the parameter in this way, especially the G22 is 10 times larger than G11. So now the mass of the particle 1 and particle 2 are different. That means the frequency are different. That's why it tends to give a non-trivial frequency, a non-trivial superposition. So we conclude that non-trivial superposition can be a proof of a multiple particle with hierarchical couplings, because without such hierarchical structure, we don't get any non-trivial superposition. But however, it is fair to say such hierarchy seems to be unnatural from the viewpoint of model building. So anyway, this is a result of case 1. So okay, let's move to more interesting situation, case 2. Case 2 contain mixing, and just for simplicity, I choose a universal coupling constant in this way. And I introduce the purple color to denote the mixing term, S12. So as I said several times, if there is a big hierarchy between mass, the right mode dominate, I omit this situation and just focus on the degenerate case. So, and remember the expression of the mixing terms. We found it contains two kinds of frequency, high frequency and low frequency. And I say the low frequency is specific to the March field system. Actually, in the degenerate limit, where mu1 equal to mu2, we have analytically shown that the coefficient of each frequency satisfies this kind of relation. So you can see this ratio is quite small. That means the low frequency mode always dominate over the high frequency mode in the degenerate limit. So we can conclude, the total signal is characterized by the low frequency mode or large wavelengths, which is determined by the inverse of mass difference. So you can see several examples. I changed the mass of particle 2 in this way, 2.1, 2.3, 2.5. Then in all of the figure, you can see the green line and the purple line overlap. That means the total signal is determined by the mixing one, S12. And yeah, all figure have the large wavelengths as expected. And because of this structure, we can use this to disentangle the degenerate spectrum. By the last comment, I mean, if we could detect this kind of behavior, then we could understand there exists a degenerate particle around Hubble scale. Okay, let me summarize my talk. We have investigated the large particle effect on cosmological collider. And we found two kinds of feature in the system, one the superposition and another one the mixing effect. And for the superposition, although it is a rare case, but the non-trivial waveform appear when there exists a hierarchy in mass and coupling constant. And for the mixing effect, I have to stress this kind of effect exists in general. And we found that the total shape function is characterized by the large wavelengths, which is given by the inverse of the mass difference when the masses are degenerate. And also we found that this kind of structure can be easily specified. So it can be a proof of existence of degenerate particles. For the final comment, I didn't touch. So let me stop here and thank you very much.
Thanks, Shuntaro. So any questions or comments? So Takahiro, please go ahead.
No, I just clapped the hand, but it's very interesting talk.
Okay, okay. So any other questions or comments? So this, if there are multiple particles, it also depends on when each particle is produced, timing of the dominant production time.
Yeah, I think it's irrelevant because in the calculation, we average the time, I mean the integral created time. So in that sense, yeah, we get the result after averaging.
Okay, I see. But once you care about these details of interaction.
Yeah, interaction is important. Actually, I didn't touch this talk. Actually, implicitly, we assumed non-derivative coupling here. But actually, in the paper, we also searched about the derivative coupling. But in that case, we found this kind of mixing effect disappear. So the interaction is very important, and our result at this stage depends on the detail of interaction.
Okay. Any other comments or questions?
Can I
just do. Oh, yeah, go ahead.
Sorry. Yeah, very nice talk. I just had a quick question. So here you had a scalar field fields in the diagram. Is there anything else that can happen if you have like higher spin fields, something with the angular dependence?
Yeah, that's a very good. Yeah, that's very good question. Actually, we haven't yet, but actually, we initiated this work to explore the supersymmetry from the cosmological collider signal. Then, in this case, we need to calculate the fermion signal also, and we compare boson and fermion. And the important thing is whether we could find a non-trivial interference between them. So in that sense, the extension to spinning particle is very important, but yeah, actually it's still work in progress. And yeah, it's very good point.
Okay.
Yeah.
Thank you.
Thank you.
Thank you very much. So about the time to ask the next speaker, but thank you very much for nice talk and keeping on time, Shintaro. Okay. So the next speaker is Fumio Uchida. Fumio, can you put your slides?
Do you see my screen?
Yeah, correct. Yeah. And Fumio is going to talk about the primordial magnetic field. Let's get started.
Yes. Thank you for the introduction. I am a PhD student at Rescue University of Tokyo, and today I'm going to talk about this paper. To begin with, I start from the introductory part. As we all know, the Earth has its geomagnetism, and the Sun also has its heliomagnetism. And not only these examples, but also every astrophysical object. An extreme example may be magnetars, for example. Every object has its magnetic field at the scales from 10 kilometers for magnetars to 10 kiloparsec for galaxies, and even larger scales for galaxy clusters and so on. And what is interesting on top of this is magnetic fields, that is so-called the IGMF, exist even in voids where astrophysical objects locate very sparsely. And before talking about what is interesting about the IGMF, let me shortly explain the observational side. I mean, how one can be convinced about the existence of the IGMF. Suppose that we are here and looking at a blazar which emits TeV photons along the line of sight. In that case, some cascading process inside the voids occur and secondary GeV photons are produced. However, according to the gamma ray observations by the Fermi collaboration and some Cherenkov telescopes on the ground, GeV flux is too faint compared to the flux in the TeV range. The reason for the absence of GeV photons is thought to be the IGMF, because magnetic fields in voids bend the path of these electrons and positrons away from the line of sight. And the latest lower bound on the strength of the IGMF is here, 10 to minus 16 Gauss at the scale of 1 megaparsec. Now let's see what is interesting about the IGMF. Since any astrophysical processes, which are very complicated, do not affect so much the evolution of the IGMF in voids, so the origin of the IGMF would be in the very early universe, and we can extract the information of the early universe from the observed properties of the IGMF. This is interesting and related to theories, for example, about magnetogenesis during inflation with like phi FF tilde or FFF coupling. And in this talk, I will give an answer to a general question. When is the primordial magnetic field as the origin of the IGMF generated? The next part is about the key mechanism, which gives the answer to that question I mentioned just in the last slide. The physics behind the mechanism is the chiral anomaly in the standard model of the particle physics. This is the anomaly of baryon number current originating from the fact that the standard model is a chiral theory of the left-handed and right-handed fermions. And here is contribution from SU2 gauge fields, and here is U1 gauge field. These gauge fields, especially W3 and Y, are mixed by a parameter theta W and leave just one massless U1 degrees of freedom, A mu, which is, of course, the electromagnetic fields. And let us substitute these expressions into the anomaly equation and set massive degrees of freedom to be 0, then we get this equation. Here, A dot B is called magnetic helicity density, and its time derivative is E dot B. In the symmetric phase of the universe, when the cosmic temperature is higher than the order of 100 GeV, and the Higgs wave is 0, in that case, theta W is constant, and the value of it is 0. So this term is 0, and E dot B is also close to 0 because of very large conductivity of the universe, since E dot B is proportional to the inverse of the electric conductivity. And in the broken phase, on the other hand, weak mixing angle takes the same value as the present value theta W naught, and both terms here and here are 0. However, something happens during the electroweak phase transition, and this paper takes into account the sourcing effect of baryons due to the non-zero values of the anomaly equation when theta 0 is changing from 0 to theta W naught. And in addition to this, several washout effects are considered. And they found that at the end of the stage, the dominant contributions are this term and this term as the source, and the electroweak spiralons as the washout. And the resultant abundance of baryons are determined as the equilibrium solution at the spiralon freezing out, TF0, TFO. The value of it is 135 GeV, and this is their result. And here we see the proportionality with respect to the magnetic helicity density A dot B. And this leads to the generation of baryonized curvature perturbations, since if we define SB squared, which quantifies the baryon noise curvature perturbations, then this is SP squared is proportional to the statistical variance of magnetic helicity density, which is non-zero in general. And an important thing is that even if the magnetic fields are non-helical and the average helicity density is exactly zero, even in such a case, the variance of a magnetic helicity is not zero. And so the baryon noise curvature perturbations are generated. This fact is actually pointed out already in this paper. So let me summarize what I explained up to here. If we assume magnetic field generations in the symmetric phase, it unavoidably generates baryon noise curvature perturbations through the chiral anomaly at the electroweak symmetry breaking. The next step is how these magnetic fields, or equivalently, baryon noise curvature perturbations generated by them, are constrained. The constraint comes from the BBN. I mean, if baryon noise curvature perturbations are too large, the BBN would be spoiled. Let me explain this point. This paper considers the enhancement of primordial deuterium abundances. This white rectangular in the left panel is the observational one, and the blue region is BBN theory with a large baryon noise curvature perturbations. They say that if SB squared is too larger than this value, then theory and observation become inconsistent. Here, what is constrained is SB squared at the BBN. So we have to consider the evolution of baryon noise curvature, baryon distribution. We have to consider the evolution of baryon distributions from the electroweak phase transition until the BBN. And here, neutron diffusion plays an important role. Roughly speaking, baryon noise curvature perturbations within the diffusion scale, numerically 0.0025 parsec in co-moving length. The baryon noise curvature perturbation within this radius is smeared out and not constrained by the BBN. And taking into account all what I have explained, magnetic fields at the electroweak phase transition is constrained like the left panel. Colored regions, yellow and green regions, allowed strength and coherence length. And the small difference between yellow region and green region comes from the ambiguity of the spectrum of the magnetic fields, depending on the magnetogenesis scenarios. Anyway, if we reinterpret this figure in terms of the present strengths and scales, what we can conclude is that the allowed strength is far below the observationally suggested lower bound. Here is the lower bound from observation, and here is the allowed maximum. So the difference is 10 to 7 times at the scale of 1 megaparsec. And these results is for non-helical magnetic fields, but qualitatively the same for helical magnetic fields. Let me wrap up my presentation. We can answer to the question when the primordial magnetic fields as the origin of the intergalactic magnetic fields generated. the answer is like this. Because of unavoidable generation of baryon noise curvature perturbations at the electroweak symmetry breaking, generation or amplification of the magnetic fields after the electroweak symmetry breaking is necessary to explain the strength of the observed magnetic fields in galactic bodies. That's all. Thank you so much.
Thank you, Fumio. Any questions or comments? You can raise your hand or put a comment there. Do you have any idea for this amplification?
Yes, what I am thinking is the generation of generation after the electroweak symmetry breaking. For example, low scale inflation or magnetogenesis from QCD phase transition. If QCD phase transition is the first order phase transition, then there is a possibility of generating magnetic fields. Yes.
But there's an astrophysical explanation for observed strength of this IGMF. Is a common explanation?
Yes, it is possible that astrophysical mechanism amplifies the magnetic fields, but and some people are saying that it might be possible that astrophysical outflow pollutes the voice, and magnetic fields is injected into the galactic voice, even if also there is no astrophysical object inside the voice. But whether it is possible or not is unclear.
If it's still unresolved.
Yes, yes, that's
okay,
right. Yes.
Okay. Any other questions or comments? Okay, so it's the final talk of the session. So let's wrap it up. So I would like to thank all the speakers for keeping on time, and let's head to the lunch for the Asian people, people in Asia. Thank you very much.